All right, so we are looking at oxidation reduction, otherwise known as redox reactions. First off, we're going to look at some definitions. We're going to assign some oxidation states, which we've already seen before, and we're going to balance redox reactions. All right, so an oxidation reduction reaction. This is when one or more electrons are transferred. That's either by gaining or losing. It's a common process involving oxidation. For instance, photosynthesis, combustion. So, an example of this is when we start assigning oxidation states. We know that oxidation has happened, reduction has happened. How do we know? Just look at the charges. For instance, in NaCl, Cl is -1 versus a partial charge of HCl. Again, Cl is -1. All right. So things to know. More electronegative elements are assigned the negative state. Free elements have no charge. It's zero. They're happy. Fluorine is typically a -1. Oxygen, a -2. However, in peroxide, it's -1. With fluorine attached to fluorine, it's a +2. All right, and hydrogens, they can be a +1 or a -1 in a hydride. The sum of the oxidation numbers or the oxidation states in a compound is 0. So the whole point is to neutralize the whole thing. In ions, the sum equals the charge on the ion. So if it's negative, it means it's got one more electron than normal. If it's positive, it's got one less electron than normal. All right. So what are the charges on these oxidation states? So let's look. CO2. Well, we know oxygen is a -2. Carbon can either be a +2 or +4. This is a 2 here. That means it has to be double the amount for the carbon. So you got to have a +4 plus -2. All right, sorry about that. Just need to fix a little bit. So let's look at this. SF6. So we know sulfur has to be at least a +6. Fluorine is going to be a -1. Fluorine is in group 17. It's typically a -1. Okay, NO3. This is a little tricky because remember, you have the oxidation state of the whole component, like the whole polyatomic ion is negative, which means it has one more negative than it does positives. So oxygen is going to be the -2 with a nitrogen of +5. Magnesium and hydrogen. Again, this one is a little tricky because you have the -1 for the hydrogen, +2 for the magnesium. Now, going back to the NO3, like Miss Co, why is this a -2 and that's a -5? It doesn't equal out. It doesn't work. Well, -2 times 3 is -6. That's one more negative than this. If we look at the same thing at the magnesium and hydrogen, -1 times 2, -2, -2, +2, cancels out. But what about this one up here? Well, because that's a +6 and that's a -1, 1 times 6, -1 times 6 is -6. All right, O3, that's a 0 because it's by itself. All right, chromium oxide. This one's a bit tricky. It's a +6 -2 for that oxygen. So this is 14, that's 12. That makes a -2. All right, we're not going to do this one. I'm not going to do that to you guys. Just know that it's 1, 2, and -2. This one right here, again, look, we've got that negative right there. So oxygen's usually typically a -2. Arsenic is a +3. When you equal it out, it does work. And it's 4 positive. You got your positive over here. I know this one's a little wonky because it is ammonium. So nitrogen's over here, and that's going to be the negative. We're not going to do the bottom one, just know that's that. All right, so the big thing when we look at redox reactions, an acronym to know is Leo the lion goes grr. Okay, big thing. What it stands for is Leo, loss of electrons equals oxidation. Grr, gain electrons reduces. So let's look at it. This has A with 2 negatives. It loses those 2 negatives. It becomes an A2 plus. Whereas here we start out with like a metal or a regular element, and then we are gaining 2 electrons to make a 2 negative. Remember, it's the opposite. Losing, you get positive. Gaining, you get negative. The reason for this being, if you gain electrons, you have more electrons than protons. If you lose electrons, you have more electrons or more protons than electrons. Okay? So oxidation states increase when you lose electrons. Oxidation states decrease when you reduce. Okay, so balancing redox reaction. I know it's going to seem like a lot. Just bear with it. So half reactions. For this reaction, NaZN, zinc chloride, sodium chloride, and zinc. So the oxidation half reaction, what loses is sodium, because you go from Na to Na plus. Okay, there's that oxidation. All right, so the first thing you need to do is write on the oxidation states. We're going to keep it nice and simple. I'm not going to get too rough with you guys because a lot of these ones that you're going to see are really super simple. All right, so what I have to add when I do oxidation or half reactions, oxidation half reactions, is I know it goes from Na to Na plus, but on the Na plus side, how does it get that? I got to lose an electron right here. So there on that side where the plus is, you're going to add the negative electron. Electrons are written in the half reaction to balance the charge. You got to conserve the charges. So when I do that, zinc, we find zinc is my reduction. It goes from a +2 to a 0, meaning it gains back 2 electrons, making it stable. Again, zinc 2 plus, you put 2 electrons on that side. Goes to zinc, right? And remember, we got to conserve the charge because there's 2 down here. I got to get 2 up here. How to do that? If I got to, whatever I do to one, I got to do the other. So I times the whole thing by 2. So when I do that, I got 2Na, 2Na plus, 2E. Zinc, 2 plus, 2E, zinc. Now what am I going to do? Get the net reaction. Cross out the things that are the same on each side. The electrons. Cross those out. Whatever's on, this side of the arrows stays on that side of the arrows. Add them together. Whatever's on this side of the arrows stays on that side of the arrows. Add them together. So you got 2Na plus zinc 2 plus goes to 2Na plus zinc. 2 moles of electrons are transferred in the reaction. We don't have to worry about putting the electrons in. All right, we use these coefficients to balance the original. So I'm going to plug in these up here, and I'm left with 2Na, zinc, Cl, 2Na, Cl, zinc. All right, this seems to be too much work for balancing a simple equation. But when the net ionic equation is given, which you are given, in other times you get this. You got to be able to figure it out. How do you do that? Again, just figure out what reduces, what oxidizes. You can balance it out. All right, so we know this gains 2, this one loses 2. So write out the reactions. Al Al3 plus 3, Cu plus 2E goes Cu2 plus 2E goes to Cu. There's 3 and 2 here. Because I have the differences, I gotta make them the same. You want to conserve it. I can't just pull them out of nowhere. So what I gotta do, whatever I do to one side, I gotta do the other. Figure out the least common multiple. 3 and 2, is 6. So multiply that side by 2, multiply the other side by 3. Right? So I get 2 up top with 6e, 3 on bottom with 6e. The 6e's, again, get rid of those. Whatever's on this side of the arrows, add together. Whatever's on that side of the arrow, add together, and plug it in up here. Put the 2 up here, 3 here, 2 and 3. Okay? Because Al, the aluminum, is oxidized in the reaction, it is actually considered reducing agent. It aids in the reduction by supplying electrons. Whereas Cu2 plus is the oxidizing agent, allows oxidation to happen. So I know we just said Leo goes Ger, right? So Leo loses electrons, oxidizes, making it the reducing agent. Ger, gaining electrons, reduces, making it the oxidizing. All right? Okay, real quick for this reaction. Write the oxidation, half reactions, balance the molecular equation, determine the oxidizing reducing agents, species that lost, species that gained. Okay, so let's figure out what reduces, what doesn't. First, let's get the oxidation states. Plug those in. So we got 3, 2, 2, 2, 0, 4, and 2. All right. So let's see. We got 3 plus to 0, 2 minus, 2 minus, 2 minus. Oxygens don't matter. How about this? Carbons. 2 plus to 4 plus. So I reduced, right? Or I lost 2. So I went from plus 2 to plus 4. I lost another 2. So there's my oxidation. So I'm going to write that down. C plus goes to C4 plus 4. I lost 2. All right. What one gained? So I went a 3 plus to a 0. So 3 plus on this side plus 3 electrons goes to Fe. Again, I've got to balance these out. When I go to balance them out, I multiply 1 this side by 3, this side by 2, giving me 6 electrons on each side. They're the spectators. So I get rid of whatever's on this side, stays on that side. Whatever's on this side, stays on that side. So you got 3C plus 2 plus 2Fe3 plus goes to 3C plus 4 plus 2Fe. Okay? All right, let's plug it into the original reaction. And we get this. Right there. You can't see it. There should be a 2 right there. I do apologize. Yeah, it's not there. Okay, so everything balances out when we have this. There should be, oh, there's the 2 there. That's why I don't need to, because there's already 2. If I've got 2Fe, 2Fe, there are 2 Fe's, it evens out. All right, so this is the oxidation, which my reducing agent is the opposite, so that's reducing. Reduction, it's the opposite, so whatever oxidized. Okay. What gained and what lost? What lost? The species that gained. Leo is going to be down here. Or sorry, right here. Ger, right here. All right, let's look at this one. You know what? We're going to stop right there. We're not going to do any of the other ones. If you have any questions, please don't hesitate to ask. You can scroll through these, check your work. If you have any questions, like I said, please let me know. And again, we're going to do really, really simple ones. If you want, you can slow these down. So you were just to do the green pages. Like I said, if you have any questions, please don't hesitate to ask. Hope you have a great day.